Hello, today we are going to look at equilibrium problems. It could be a wide range of problems. It's not going to be every single equilibrium problem that could be ever asked, but it should be a good range of them. So, why don't you sit back, listen in, and hopefully learn some of how you solve most equilibrium problems.
Welcome to my test review of equilibrium. And right into problem 2. Say, what is the relationship of Kc to Kb for the following reaction? Now, technically, it's kind of hard to reverse CO2 in water and put it back into methane. It could be done. But we want to know what is the relationship. Even though Kc might be incredibly huge to the product side, you can figure that out. So, the relationship is Kc times RT raised to the power of the change in moles. Why? Because we're essentially saying P equals N over V, which is our molarity, times RT. And we're doing that for each product and each reactant. So if there's more moles of gas on the left, then you're going to have dividing by more RTs. If you have more moles of gas on the right, you times it by more RTs. Let's calculate the amount of gas. We need to compare the amount of gas. 1 gas, 2 gas, 3 gas. 3 moles on the left, 1 gas, 2 gas, 3 gas, 3 moles on the right. So what is our change in moles? Our change in moles is 0. So we're going to say Kc times RT to the 0. And any number raised to the power of 0 is 1. So we say Kc equals Kp. Full stop. Problem 3. So we're looking right here at Le Chatelier's principle. We're saying which change will not cause a shift towards products. So which change will cause a shift towards reactants or none at all? So we have an aqueous, goes to a gas, and another aqueous. And we're told that delta H is positive 67, meaning this is endothermic, meaning heat is a big old stinking reactant. But let's look at this. A looks at increasing temperature. If you increase the temperature, you are increasing a reactant, thus causing a shift towards products. B, adding lithium hydrogen carbonate. Since this is aqueous solution, adding more concentration of reactants would cause a shift away from the addition towards products. Then you're left with C and D. C is the increase in pressure. This will only affect gases. We have 1 gas on the right, no gases on the left. So this is essentially a high pressure, and this is a low pressure. Whenever you increase the pressure, we're going to go from high to low. So we're going to shift to the left. So there's our answer, C. But just to finish off, D. Adding an acid to react with lithium hydroxide. You can add HCl plus LiOH and forms irreversibly water and lithium chloride. Meaning that if I add an acid, I am going to remove the product lithium hydroxide and thus cause a shift to regenerate more lithium hydroxide. So definitely not D. Problem number 5. We're told that we have this reaction. Acetic acid breaks down into proton and acetate reversibly. And we're asked which way will the reaction shift if under the following conditions. If the Ka, which we haven't learned that, but essentially the K for an acid, is equal to 1.8 times 10 to the negative fifth. So remember, K is product over reactants raised to the power of their coefficients, and it's only for aqueous and gas components. All these are aqueous, they're all coefficient of 1, so this is relatively straightforward. We're told that acetate is 0.89. We're told that concentration of acid is 4.5 times 10 to the negative third. And we're told the concentration of acetate is 3.2 times 10 to the negative third. We need to plug that in. And because this is not necessarily at equilibrium, we are solving for Q. What is Q? And then we can compare that to K. So we get this, we plug this in, we get 1.61 times 10 to the negative fifth. And is 1.61 greater than or less than 1.8? So Q is less than K, meaning we need just a smidgen more products. So this will shift to the right. Answer B. Problem number 9. I asked you to determine the Kp for a reaction where chlorine gas is bubbled through bromine liquid to form bromochloride. And I asked you, what is the Kp under these conditions? Don't be fooled. Even though I give you a volume of bromine, we don't include pure liquids or pure solids in our K expression. So even though I say 500 milliliters of bromine exists where 2.5 atmospheres of chlorine and 1.89 atmospheres of bromochloride, you do not need the 500 at all. It is simply 1.89 squared over 2.5. You do that math, and you get a Kp of 1.43. Answer A. Problem number 12. I'm giving you a K and asking how much carbon dioxide is present in the following reaction if we have 1.75 times 10 to the negative third molarity of carbonic acid present at equilibrium. Once again, don't be fooled, water is not included. So we say the K for this 5.24 times 10 to the negative fourth equals, give you 1.75 times 10 to the negative third concentration of CO2. So what do I have to do? Get K, other side, get CO2 on this side. So CO2 is going to be 1.75 times 10 to the negative third divided by 5.24 times 10 to the negative fourth. You do that, you should get, well, you should have 3.34 molar CO2. Relatively straightforward. Finally, we have our dreaded ice problem. This is based on a lab we will be doing in a few weeks. Looking at we have initially 5 mils of 2.5 times 10 to the negative third molar iron, mixed with 5 mils of 2.5 times 10 to the negative third molar thiocyanide, and we generate 2 times 10 to the negative fourth molar iron thiocyanide at equilibrium. What is the K for this experiment? So, this one is a little bit harder than what we will see in most things, because we are given a molarity of iron, but we're diluting it by a factor of 2. We're taking 5 mils and we're saying M1V1 equals M2V2, or M1 is 2.5 times 10 to the negative third. We're using 5 mils, but we are diluting it with another 5 mils to make it 10 mils. So in both iron and thiocyanate, we have to divide by a factor of 2. To get it, 1.25 times 10 to the -3rd molar. Before the reaction occurs, though, we still have 0 thiocyanate, iron thiocyanate. Now, at conclusion, we always change by a factor of our coefficients. Minus x, plus x. So making this one 1.25 times 10 to the -3rd minus x. 1.25 times 10 to the -3rd minus x. And this one being x. But I also give you, at equilibrium, after dilution, mind you, x is equal to 2.0 times 10 to the -4th. So we know x. We can calculate x. It's given. So 1.25 times 10 to the -3rd minus x is actually 1.05 times 10 to the -3rd. And that is also 1.05 times 10 to the -3rd. With that in mind, we can now plug our 3 values back into our initial k expression and solve for k. So 2 times 10 to the -4th divided by 1.05 times 10 to the -3rd squared. I could do it twice, or I can just square it. It's the same thing. You get 181 as your k. And this concludes my review on equilibrium. Thank you for your time.